Hello everybody, in this lecture we will be solving 1995 IMO problem number 4. Here is a view of this problem. We would like to find the maximum value of x sub 0 for which there exists a sequence of real numbers with the following conditions: x sub 0, the initial starting point, and x sub 1995 are equal to each other, and furthermore each subsequent term is defined recursively by this relationship. Okay, so let's start by first seeing if we can find a simpler form. So this thing, we can just find common denominators and expand it. We would get x sub I times x sub I minus 1 squared plus 2, which is equal to x sub I minus 1 times 2x sub I squared plus 1. Expanding and moving everything to the left hand side, we would get x sub I minus 1 squared plus 2x sub I minus 2x sub I minus 1 x sub I squared minus x sub I minus 1 is equal to 0. Then I will bundle terms together. I will bundle this one and this one, and then these two together. So that would further give me, from these two I would get x sub I minus 1 times x sub I minus 1 minus 1. And then here I would get, so let's factor out minus 2x sub I. So we would have x sub I minus 1, x sub I minus 1 is equal to 0. These terms are common. We can further group them together. So therefore we would have x sub I minus 1 minus 2x sub I times x sub I minus 1 minus 1 is equal to 0. And now finally, what this means is that we have a product whose value is equal to 0. So this would imply that either, let's write it carefully here, either the first guy is equal to 0, in which case x sub I can be recursively defined as x sub I minus 1 over 2, so the preceding term divided by 2, or the second one, in which case x sub I again can be written in terms of the preceding term by this relationship. So each time we progress from x0 to x1 to x2 and so on, we need to comply with one of these equations, right? So we are bound by one of these relationships. Having noticed that, then we can focus back on what we need. So starting from x0, we want to go back to x sub 1995, and I would like to start by the following observation. So I would like to make it into a claim. I claim that if a sequence is to have the two conditions given, conditions given by this sequence, then this sequence has to have at least one x sub I, at least one x sub I is equal to 1 for our sequence. So x0, x1, and so on, x1995. So that's the only way that this sequence will be such that the first term and the last term are equal to each other, and then the sequence is governed by the given, well, this one, this new relationship that we got. And the proof is quite interesting. So consider a partition. Well, first let's assume to the contrary, right? So let's assume to the contrary that no x sub I is equal to 1 for I equals from 0 all the way to 1995, and I would like to show that would lead to a contradiction. So let's partition the set, the positive real numbers with the exception of 1 into the following. disjoint union, 1 over 8, 1 over 4, open bracket, and then close bracket, 1 over 4, 1/2, open union, 1/2, 1, open union. Now this one is interesting. I'm gonna jump the 1 because I'm excluding it. I believe no value, no x sub I in this sequence will ever hit the 1. And then I have an open interval and then back a closed interval, union, open interval 2 to closed interval 4, and then I open it, and so on. So I think the idea is clear. So what I claim is that all the x sub i's in this sequence, these 1996 terms, are all living in some sets in this partition. Well, it turns out, before I go further, let me color code these intervals. I will produce two colors, namely the red color, and then the red colored intervals, and let's say the green colored intervals. So I alternately color these intervals in this following fashion, and then I claim that this recursive form this, of defining x sub I, each subsequent x sub I, by this manner implies that the consecutive x sub i's in this list, right, they would fall on onto different colors, right? So wherever x0 is, I don't know where it is, so let's say here I claim x1 will hit a red color, and then x2 will be back to a green color, and so on. But then that would be a problem, because if you start with x sub 0, so the even indexes will have green and the odd indices will have red, but then 1995 is an odd number index. As a result, it will have a different color interval. So therefore, let alone, forget about being in the same value, they don't even live in the same interval. So just as an example, so for instance, let's say that x sub 0 is, let's say, 1/3. So 1/3 is in this interval here. Now let's see how this definition governs what x sub 1 will be. If it happens that we pick this one, this equation, x sub 1 would simply be equal to 1 over x sub 0, so that would be just equal to 3, and sure enough 3 lives in this interval. So we started with a green interval, we ended up in a red interval. Alternately, it can be here, so that's one idea where it can be 3, or if it's governed by this equation, we would have 1/3 divided by 2, which is 1/6, and boom, x sub 1 in that case would be in that red one. So I just leave it to you as an exercise to see that this really is the mechanism behind it. So we have picked the intervals, this partition of disjoint sets, one end closed, another end open, up to 1, and after 1 it's one end open, the other end closed, and that's this coloring scheme clearly shows that there is no way, if x sub i's are governed by this, that x sub 0 and x sub 1995 would be equal to each other. As a result, so this is the desired contradiction, implying therefore that in fact there exists an x sub I which is equal to 1. Let's call it x sub k for that matter. Now in fact, this gives us a huge idea on how to approach the problem and find the optimization that we need, and we need to find the maximum value of x sub 0 by noticing that, for example, if x sub I is part of an interval, let's say this closed interval 1 over a, then it implies that x sub I plus 1, regardless of the equation you pick, will be, so x sub I plus 1 would be definitely between 1 over 2a at the least, right? So 1 over 2a, this is the worst thing that can happen. So let's do it in two steps. So x sub I plus 1, if it is in this interval, so we divide by 2, so that would be this interval, or x sub I plus 1 can be x sub I plus 1 can be in the interval, and this is close to, by the way, that's a 2. It can be in the interval where we reverse it, so 1 over a reversed is a, and then a reversed is 1 over a, so it's still in the 1 over a range. So you can clearly see here that the least of these numbers is 1 over 2a, and the largest one is a. When you look at what might be the case for x sub I minus 1, now the thing will be, so the x sub I minus 1 expressed in terms of x sub I would be 2x sub I, so therefore if we follow this one, 2 times x sub I would be 2 over a and 2a, or it would be defined by this one, so which is 1 over x sub I, so or x sub I minus 1 is, so 1 over means between a and 1 over a and a again. So now what I'm trying to say is that when you compare these two, if we bundle them together, these two bundled together would imply that x sub I plus or minus 1 is always, for sure, between the least of these numbers is 1 over 2a, the highest of these numbers is 2 over a, right? So among all these 4 intervals, so 1 over 2a up to 2a. So this is with a certainty. Now let's therefore, we can generalize this result pretty quickly for our guy x sub k. So we know that x sub k is equal to 1, which would lead to x sub k plus or minus 1 being in the interval 1/2 to 2, and then in a similarly x sub k plus minus 2 will be in the interval 1/4, 4, and so on. So x sub k plus or minus j would be in the interval 2 to the power minus j time 2 to the power j in this interval, and for all j, for all j, for which, let's write it like this, for which x sub k plus j, x sub k minus j are defined. And in this particular case, what I mean is that for the indexes, so for instance for k plus j, we need to ensure that k plus j do not exceed, i.e. k plus j is less than or equal to 1995, and also k minus j is greater than or equal to 0. So therefore, rewriting these, so for instance this one here would put an upper bound for the j, and in a similar way this one here would put a, right, so j should be also another upper bound, j should be also less than or equal to k. So combining these two, right, so these are kind of the two extreme values that the j can take. So therefore, if we pick those two extreme values for x sub 0, because eventually I need to maximize it, right? So x sub 0 is either less than or equal to 2k, or x sub 0 is less than or equal to 2 to the power, so we are looking for the so 2 to the power j. In this case, j can be as high as 1995 minus k, and we would navigate between these two numbers, and obviously we want to end up at 1995, right? So therefore we can combine these two things together and say that x sub 0 is less than or equal to 2 to the power m, where m is the minimum, because both of these should be satisfied, right? So what is the maximum is the value of x sub 0 which would satisfy both of these conditions, k or 1995 minus k. And this number, as you can see here, would definitely be less than or equal to 997. Okay, so the maximum, therefore the maximum value that x sub 0 can take would be 2 to the power 997, and this would be attained. So you can think, is this does this work? Yes, it does. So if you start with x sub 0 as 2 to the 997, x1 you can pick it by dividing it by 2, 996, and x2 would be 2995 dot dot dot, oops, all the way to up to x sub 997, which will be equal to 2 to the 0, which is 1. That's great. So that's our 1. So which is the condition of this claim here. And then we can keep further. So x sub 998 would simply be equal to 1/2. And we continue in this fashion. And finally, x sub 1994, I should say, would simply be equal to 1/2,997. Finally, x over 1995. We will switch the rule. Instead of keep applying this rule, that's what we've done. So term after term, I applied this rule. Now I will apply the last rule, and that would give us, when I flip this, it would give us 2 to the power 997. But wait, this is just equal to x sub 0. So we have found such a sequence. So it is attainable. So this maximum is definitely attainable. And that finishes the proof. I hope you enjoyed this video, and looking forward to see you guys in our next lecture.